Welcome once again to the physics video lecture. This is Psci 168, video lecture 19. So let's get started. We're in the middle of, or actually towards the end of the hydropower discussion. And there's a midterm exam coming up, and I'll say something about that at the end of the hour. Because there are no surprises, I'll pretty much put up what you're going to be expected to know. But let's go to the hydropower once more, draw our cartoon, and I'll set up a problem, an exam type of problem for you guys to solve as well. So let's see, we want the water to be blue. We've got the dam holding the water back. Had some nice images of dams on recent homework. Okay, so there is our water. We have a penstock that carries the water down to powerhouse. And now we have some mountains in the background too. In the winter they have snow on them, in the spring the runoff fills the reservoirs. We have a lower reservoir, and as we saw the other day, we may have a third and a fourth and a fifth one downstream. But it's always this height difference H that measures the potential energy of the water in the reservoir. We also have the concept of the pumped storage, where we actually need energy from out of town, so to speak. So these are some towers that carry wires. Okay. And bring power into our power plant right here. So we can actually get power from out of town, and maybe we need to draw some kind of power plant here. There's a cooling tower, and there's something here, maybe with a smokestack. Okay. So we've got a power plant out of town, and there's a transformer substation. And we can bring power in, energy in, and actually pump water up the hill, and that's how we would store the energy. So that has to be mentioned as well again, the pump storage idea. We also had the water cycle. So there's the radiant energy from the sun, which evaporates the water and carries it up into the mountains in the first place, or up into the clouds. So we had that water cycle here as well. So you can see the picture is becoming pretty rich. So we got the water cycle. We have our solar energy, because that's the sun for you. Okay, solar energy. And because we have the evaporation here, we're going to have to study that. That's thermal physics. That's coming up later. This power plant here as well. So power plant. This could be gas, coal, oil, nuclear. All of those things would be a possibility. And what I'm showing here is either delivering, well actually here I'm showing bringing energy in to do pumped storage. Okay. Very crucial to note that it's not that we just get the energy and then save it and send the water back up the hill. We're getting the energy from out of town to do the pump storage. Okay. So what else do we have there? We got the water cycle, we got solar energy, we got evaporation. So all of these things over here refer to thermal physics coming our way soon. that's going to be our next major emphasis, going to be thermal physics. I'll just put that in parentheses right now. But then back to our hydropower idea, we have the following. We have the energy stored, capital W, MGH, mass of water, G, height difference here. Remember, everything in kilograms and meters and seconds, okay? We have the mass. I'll use the uppercase here, although we have to be confident using either. But that way I can remind us that the mass is the density times the volume. And we have that in our notes, right? Density times the volume. And then we have the power formula is that flow rate. I'm going to make up a little more room here. And also note that we can talk about this potential energy in terms of joules, of course, or kilowatt hours. So we had a problem on that. That's a really nice thing to be able to convert to kilowatt hours, because we have some idea how many kilowatt hours we need. Okay. So if you know how many you need for your household, you can just multiply 1 million, and then you know how many you need for 1 million households. Okay, pretty basic. Yeah, so we have that, and then we have the power formula. And this is in watts. It's that flow rate times G times H. And finally, we also know that very generally, power equals energy per time, joules per second. And you want to be able to use this equation in any of the 3 different ways. So that means that energy equals power times time. And that also means that your time, if you solve this equation for time, it's energy divided by power. Now this last one is important if you want to know how long is it going to take for this reservoir to run dry, for instance. Okay, so you're running a certain amount of power, and you know how much energy you had in the first place. How long is it going to take to run dry? All of these things, of course, are in consistent units, so you're going to get seconds out of this, right? You're going to have joules per second, which is watts, and so forth. So let me formulate one problem, which will be exam type problem. And you guys can give it a try. If you have questions about it, ask me, I can solve it for you. But definitely give it a try first. So we have, this is a hydropower problem. So let our volume be 1,000 meters times 500 meters times 50 meters. Or how about 20 meters? I'm choosing some nice numbers here. But that's the volume of a reservoir. And you have to know the density of water. It's in your notes, 1,000 kilograms per meter cubed. And we're going to let H be equal to 400 meters for our scenario there. And we'll let M over T, which is the flow rate, be, going to make up a good number here, 20,000, 2 times 10 to the 4th kilograms per second. It's a big pipe, but these pipes are big. Okay. 2 times 10 to the 4th kilograms per second. And the question is, find energy in the reservoir. So energy stored. Write that little meter. So we want to find the stored energy. We want to find the power that we're getting with this, right? There's the power formula right there. Okay. Power in watts, which is what you're going to get. And the third question is the time for that reservoir to run dry. How long would the reservoir run using that power? Time for the reservoir to run dry. You know, if you can solve a problem like this, you can solve any problem. These are just different numbers. This could be a small scale, medium scale, large scale. So yeah, that's the type of problem I want you guys to be able to deal with. Also on the exam, you want to be able to outline all of these ideas, you know, be able to draw the cartoon and what it means. Okay. So let's see where we want to go with this. We're not quite done with the hydropower topic. So we've talked pumped storage. That's on our list right here. If you were pursuing the, so example, that North Fork of the Kings River project that I wanted you guys to look at. North Fork of the Kings River. If you're consulting maps and you have a good map, you actually find on the map the location of some of these objects. For example, obviously where the dams are you'll find, but you'll also find where the aqueducts are that carry the water from one dam to another. Because in reality, we have a dam here, and then maybe there's 10 miles of mountains, and there's another one down there. Okay. So those will actually be marked on the map as aqueduct. And that's what our next section is going to be about. I want to spend a few more minutes talking about aqueducts. Now, again, I'm going to send you guys out to look them up, get some great pictures. I'll just do a little bit of explaining. So, you know, we can actually leave this picture up and erase this board now. Okay, so our next topic that will complete the whole hydro discussion is about aqueducts. So here we go. Aqueduct. That's a device for carrying water from one place to another. Here's what I want you guys to look up. First of all, the Roman aqueduct. And of course we want images. Okay. We want images, and if you look this up, you'll be amazed. So with the Roman aqueduct, Rome is over here somewhere, and there's some other cities of classical antiquity, and they have to bring in a steady water supply, so they build a very gradually sloping channel. water is carried from the source, mountain somewhere, all the way to the city. And so obviously your surveying has to be pretty good, because that grade has to be pretty even and gradual, because you want it to go for miles and miles. And what you'll find is that there were channels that were underground. They come to a valley, with a river going through it. So here's a river valley. And then they have to build some of those famous aqueducts. Actually, they would do a few courses of arches. You want to look some of these up, but you've got the Roman arches and another course of arches. Your pictures will be better than mine, okay? So yeah, they had a sloping channel, and they had these amazing bridges, aqueducts to just maintain that channel. There's another thing that I want to mention, and that is if you have a valley that for some reason you don't want to or can't bridge, there's a thing called a siphon, an inverted siphon. So the channel actually goes down as an airtight pipe. So let's have our water sloping down here, okay? So this one here, as long as this level is lower than the level here to the left, you'll actually get a continuous flow. And then you don't have to bridge the valley. So sometimes you bridge the gap, sometimes you run what's called an inverted siphon. Inverted siphon. Okay, so if you look up Roman aqueducts, you'll be amazed. You'll get some great pictures. You may already have some of those back from when we were talking about the arch, okay? Because that's where some of the most beautiful examples are. Like I said, my picture is not the best. So the next thing, so that's a couple thousand years old. The next thing is we want to look into is the Los Angeles Aqueduct. Okay. So the Los Angeles Aqueduct, that was built around 1908 to 1913 or so. Look this up. Very famous in California history, actually. I will draw a map. Before I say it, so sloping channel, we say it's gravity driven. Gravity driven. And it turns out the Los Angeles Aqueduct is also gravity driven. So now I'm going to do a little freehand map of California, just for some orientation. And you guys will find some very nice maps online. You print something out that looks good and that clarifies the situation for you. So let's see if we can remind ourselves what does California look like. Roughly some shape like this. Right here's Lake Tahoe. So LA would be down here in my picture. Growing city, not that much water. So in 1908, they bought up a bunch of land. Okay, wait a minute. First we got to do the Sierra Nevada again. So the mountains that we were talking about the other day are here, and over on this side is the Owens Valley, and on this side we have the Central Valley. Okay. Central Valley, Owens Valley is the high desert valley. So they did a gravity-fed aqueduct, and by the way, there are mountain ranges here. blocking LA off from Northern California. So let's take another color here. So they did a gravity-fed aqueduct all the way to Los Angeles. That included open canals, closed canals, tunnels, bridges, inverted siphons, and everything. Gravity-fed. Pretty amazing. So that's our Los Angeles Aqueduct. Okay. So yeah, you want to look some information up on this. You'll be impressed, because that's quite the distance there, all gravity fed. Now the third aqueduct you should be aware of is the California Aqueduct. And again, you'll find good images and good information on it. This was built much later, 1960s perhaps. Dates, okay. And the California Aqueduct comes in from the Sacramento Delta and goes over these mountains into LA as well. There's another one that comes in from the Colorado River we won't mention right now, or we won't get into. Now the interesting thing about the California Aqueduct, pen's done, is that it's not gravity fed. Okay, you're starting out at around sea level and you're ending up going over a very high mountain range. So there is pumping going on, and there are pump stations along the route. So you've got a channel that's gravity fed, and then eventually they'll boost it by, say, 50 meters or 40 meters or something, and they'll let it gently flow downhill. It goes all the way down the Central Valley, or that's right, the west side of the Central Valley, and then crosses the mountains here north of LA. So what I want to say about this is it's not entirely gravity driven. So it takes quite a bit of energy to pump these enormous amounts of water up over the mountain range here. Yeah, make sure you know we have mountains here. But what's the formula for pumping water? P equals M over T GH. Okay. So this is the same formula for pumping water over the mountains that we're using for our hydropower. In this case, this would be the flow rate in kilograms per second. Okay. That would be G, and that would be the height of the incline over which it has to be pumped. So you would actually be able to, just by knowing the parameters of the system, how much flow, how much water are they trying to get over, how high is the step that they're pumping it up, you can just calculate immediately how much power is needed to do that. Okay. And so again, you want images for all of these, images and maps, because that'll help you orient yourselves as to what's actually going on there. Okay? So here's the progression. You got the Roman Aqueduct, where a lot of this stuff was developed, and then you've got your Los Angeles Aqueduct from the eastern side of the Sierra Nevada, all gravity driven. There are some reservoirs in between, there are mountain tunnels, there's everything. Okay, then you've got the California Aqueduct, which is the most modern, which uses enormous power to pump these enormous volumes of water from basically sea level here up the valley. The valley increases in elevation down towards Bakersfield, and then over the range down into LA. So I think that's where we're going to leave it. This will round out your whole presentation pretty nicely. So once again, images, dates, maps for all of these projects. Next time we'll start talking about thermal physics, and we'll see you then.